Another common application for integrals involving work is pumping fluid from a tank. So, as fluid is removed from the tank, the distance that fluid must travel to get out of the tank is increasing, which makes the amount of work to move the fluid out of the tank increase. And in some of these questions, the shape of the tank can vary, which is going to affect how quickly the tank empties. We'll get to that when we get to that. So for now, let's just work with a very simple cylindrical tank of water. Okay. Now, I pulled this from the textbook, and the author there chooses to use X in this example. I tend to orient everything in terms of Y, because what we're doing is we're going to take this slab of water and move it out of the tank through the top. So we would be moving vertically instead of horizontally, and so the Y variable makes more sense. But just to follow his examples and pictures here, we'll use X for the time being. Okay, so effectively, what we want to do is we want to find out, so for this upper slab of fluid, or water in this case, we want to know how much work is going to be involved in moving that fluid out of the top of the tank here. Okay, now this is going to have some sort of volume to it, okay, and we can use that volume as a predictor as to how much it weighs, and the weight of this water is basically what we have to overcome in order to move it out of the tank, so to basically pump it out of the tank, that is. So common measurements here, the weight density of water is 9,800 newtons per cubic meter. So that's effectively the density of the water, but affected by a gravitational constant. So the density of water is 1,000 kilograms per cubic meter, but if we multiply that by gravitational constant of 9.8 meters per second squared, then that changes from a mass to a mass times acceleration, which is a force. So that's why it's 9,800 newtons per cubic meter. In other units of measure, 16 cubic feet per second squared. So one of our jobs here is basically to figure out what the volume of one of these slabs of water is. So if we think about the tank as it's emptying, there's going to be multiple slabs of water. So if we remove this one, then the next slab of water might be the one right below it, which is this one right here. All right, so the thing is, we're going to remove one slab at a time and then calculate the weight of each slab, which we would need the volume, and then we'd multiply that volume by the weight density. So, volume of the slab. All right, to do that, what we have here is the top of the slab is a circle. And so the area of a circle is going to be pi times its radius squared. Okay. Now, to change this into volume, we have to multiply that by a height. All right, so it's going to be pi r squared times a height, and in this case, the height is the difference between the water levels. You know, if we're not doing this on an infinitesimally small scale, we think about like, what's the volume at an initial time? Then we pump out for, say, a minute. Then what's the what's the height of the fluid at the initial time? And then what's the height of the fluid after 1 minute? And we can use the difference in height to represent, the height that was removed, allowing us to get the volume. So this might be like x of I might be the height initially. And then this might be the height after a specific period of time. Which all is to say that delta x is the height of that slab. Okay, so that gives us the volume of the slab. Then the force, if we take the weight density, which is in newtons per cubic meter, and we multiply that by a volume, which is cubic meters, then we're left with newtons, which would be force. So the force here is going to be, in general, the weight density times the volume. Now, if you think about work being done is a force happening over a distance. And so we can calculate the force required to move this slab of water, but then we have to see how far it has to travel to get out of the tank. So that's the last part of this. So whatever the current water level is, that's how far it has to travel to get out of the tank. And the thing is, that's going to change. So this dark blue water level is higher, so it's going to, take less to pump it out. All right, then the next water level is a little bit lower, so it's going to take a little bit longer to move it out. So it's going to change through time. So that's why we need to use integration here, because the number one, the tank shape can change, which would mean that we would have to get an approximate amount of work that would take each slab to move. But then also, because the depth changes, we need to approximate the amount of work at each level, add up the total, and then that's going to give us the approximate total work. So the total work is approximately the force times the distance that it needs to be, so that's the work on each interval, and if we add that up over all the intervals, that will give us the total work altogether. Okay, so general process here. The things that we need to know in order to calculate the amount of work in these kind of situational problems. First, we need the weight density of the fluid, and that's usually just given in the problem, so that's generally not an issue. The area of a horizontal cross-section, which is going to be multiplied by dy to make a volume. So we called it volume before, but here we're looking at cross-sectional area. And then the distance that the fluid must travel to exit the tank, and then that's effectively just going to be the total distance that it needs to travel to get out minus y. Let me help you understand why that is, and then we'll work an example together. So let me draw another canister here. Okay, so here is some type of tank, and it's filled with a fluid, and I'm just going to say this is the top layer of that fluid. Okay. Now, we want to move this top layer of the fluid out of the tank. Now, when we think about pumping this out of the tank, essentially what we're doing is probably like putting some sort of gas like inside the tank, and then that adds pressure to the top layer of water, and then that pushes the bottom layer of the water out through the top. And in some example problems, there's an additional pipe that it has to go out, but effectively, you kind of have this pipe that would be all the way through, and this water, as you increase the pressure above it, pushes through the pipe and out through the top. Okay, so it's effectively going to happen in like the opposite way that we picture this happening, but that's okay. The total amount of work is going to be the same. So, as I said, I prefer to use the variable y. So this slab is going to be dy. So we called it delta x before. It's going to be an infinitesimal quantity when we take an integral. All right, now, so let's call this, of course, my top of the tank. And this would be the current water level. And the current water level is going to be the variable y. Okay, I'm just going to keep track of that through the variable y. And that way, we can always refer to it. Now, if there happens to be some additional distance that it must go out, so this is some additional pipe, okay, then let's say the top of the tank is, I don't know, 10 meters, and it has to go out an additional 5 meters. If the current level is y, then we're basically going to take whatever this level is, it's got to travel, let's say it's at 5, all right, and then this is 10, and this is 15. All right, so this is at height 5 meters. It's got to go 5 meters to get to the top of the tank, and then 5 more meters to get out. So it's got to go 10 meters total. So the total distance minus its current level. So that's what I'm trying to show there. All right. Now, the total amount of work done here, we can find this by integrating, as we said. And it's going to go from the lower level of the fluid to the upper level of the fluid. Sometimes these examples, the tank isn't completely full. If it's only half full or something, for instance, then you would integrate from the bottom of the tank, which is always going to be y equals 0. That would be your lower level. And then the upper level would just be how full the tank is. Okay. Then you're going to multiply by your weight density. All right, and that's going to multiply the area of a cross section. So just a cross-sectional area of the tank at any point y, and then the distance that it has to travel to flow out of the tank, dy. And this sets up everything that we mentioned before. All right, so the area times dy gives us a volume, all right? Then volume times the weight density gives us a force. Force times distance gives us work. All right, so let's walk through an example problem so you can see how this is effectively done. All right, a cylindrical tank that's 12 meters tall and has a diameter of 8 meters is buried underground so that the top of the tank is 4 meters from the surface. All right, let's go ahead and draw a diagram here. All right, so it's a cylindrical tank, so these are usually the easier examples to work with. All right, and it is situated that it's 4 meters underground, so we have ground level here. And this distance here to here is 4 meters. It's 12 meters tall. And we have a diameter of 8 meters. Okay. We want to find the amount of work necessary to pump a fluid that has a weight density of 4,500 newtons per cubic meter to the surface. Now it's not indicating that the tank isn't full already, so we'll just assume that it's completely full to start with. But I generally draw like a cross-sectional area about halfway just for illustration's sake. All right, but this right here, I need to get, that's my top level of fluid, and I need the cross-sectional area of that. So we'll get that in a second. Integral that we just learned, the work will be the integral from the lower level of the fluid, which is at y equals 0, to the upper level of the fluid, which is at y equals 12, because we're assuming it's completely full, because they didn't say otherwise. Then we take the weight density, which is 4,500 newtons per cubic meter, and then that's going to multiply the area of a cross-section. So the nice thing about this tank is because it is cylindrical, the cross-sectional area is constant all the way through. So it's pi times a radius squared. Well, the radius of this is, since the diameter was 8 meters, the radius of this tank is 4 meters. So pi r squared, so 16 pi. Okay, and lastly, we need to figure out the distance that this fluid needs to travel to get out of the tank. All right, so if we think about this, it's not completely pumped out until it reaches ground level, okay? So if we think about the bottom layer, it's got to go through 12 meters to get to the top of the tank, and then an additional 4 meters to get to ground level. So the total distance that the fluid's going to have to travel is 16 meters to get out. All right, and then we just subtract the current water level, because each water level is going to be different. So like for instance, the top of the water only has to travel 4 meters to get out. 16 minus 12 is 4. The middle at 6 meters would have to go 6 meters plus 4 meters would be 10. 16 minus 6 is also 10. So checks out. And then we're integrating dy because we're orienting ourselves vertically here. Okay, now it's just fine to use your calculator to come up with these results here. And it's really preferred because oftentimes these numbers can get fairly large. It's like this is 72,000 pi times the integral from 0 to 12 of 16 minus y dy. So that integral value, 0 to 12, 16 minus, I'm just going to switch that to an x, dx. So that's 120. That's going to get multiplied by 72,000. Then that's going to get multiplied by pi. So, like I said, sometimes these numbers can be inflated. But it looks like 27,143,361 joules. Oops. And oftentimes with numbers that large, you'll just round to the nearest integer, but follow the instructions in your homework.